Hello and welcome. It's the same day. I just put on a sweater because I got a little bit cold. So, we're moving into part B of this video. We just completed part A. So, this time we're going to take some of these specifications and actually the whole entire reaction from the first homework, part C. If anyone has questions on that, feel free to go back and watch that video. But we're going to be using a tubular reactor this time. And we're going to discretize this just like part 1, but into 200 perfectly mixed sections. And then to do this even more efficiently, we're going to use things like jacks and Jacobian and jet and things like that. And then from here, we're going to create some plots of concentration and temperature profiles through the tube. Excuse me, I keep hiccuping. Through the tubular reaction over 2 seconds, and then actually quantify some of these values. I know this sounds like a lot, but just as always, we are going to walk through this step by step and explain it as in-depth as possible. So currently, I'm going to go in here and I'm going to input the first thing, which we can take from our previous homework, which is going to be this HW2B library, which is very necessary for this. And then from here, actually, I'm going to input some of the variables and the jacks, and when I unpause, it will all be in there. Okay, I'm very sorry. My microphone may have been bugged the first 2 minutes of this video, the first like 2 minutes and 15 seconds. So I'm not sure yet. I'm going to give a really quick rundown in case it was. Essentially, we're in part B of this homework. I just completed part A. We're going to be redoing homework 1, part C, with the same conditions, but this time for a tubular reactor with 200 perfectly mixed sections, which we'll be doing back mixing again like we just did in the previous part. We're going to be using Jack's framework, and we're going to be actually creating a concentration and temperature profile through this tubular reaction over 2 seconds. And then this will help us actually plot and quantify these. Again, I'm just recapping. I don't know if my mic worked those first 2 minutes, but I know it is now. So to recap what we did, we took these variables from homework 1C along with the specifications listed in here. And this is where we've been working. So these are all the variables. This again is our CHE file library, and then these are the JAX inputs that are going to help us do this. So I don't know if that was a needed recap or not, but I'd rather it be safe than sorry. So now we've gotten to the point of actually putting our equations in, so we were able to graph actual lines. So this is going to take a while. We're going to have to input a lot, but we want this to move down here. So first, we want to define our right-hand side, which is going to be time and a vector, just like part A of this homework. And we will be working with concentration and temperature because those are the profiles we're looking for. And we want to split this data up into 2 vectors. And I need a space there. Now the next part is, since we want 2 profiles, we're going to be looking at 2 different variables with respect to time. Well, not respect to time, we're going to be taking their derivatives, so DC. And like last time, we want this zeros with respect to our iterations, which is n. And then we will put the same thing, np.zeros, n. So now we have defined the right-hand side, we have defined our concentration and temperature, and we have allowed them to actually create profiles. Now the next section is going to be using our Arrhenius equation, which is K naught. K is equal to K naught times. Now this is why we need to input all those libraries, np dot exp times negative er divided by t. Now this is the Arrhenius equation. Now again, like last time, we need to put dc and then the brackets in a 0, and then I have it up still. Maybe I don't. Oh yeah, I do. Here we go. You see, remember this part where we put our derivatives with 0 and 1. Same concept here. So we will do, this is being weird, d c 0 is equal to q cin is concentration n minus our c 0 that we just defined. This will be divided by our volume, and then minus our k value that we get from this Arrhenius equation divided by the concentration we're getting. So this is our first equation, but then we also need the derivative of the concentration from 1 on. So we get this, and for this equation we will get, again, Q, the flow rate, times, let me multiply, there we go, Q times C, which we want from infinity to negative 1, I go inside the parentheses, minus C from 1 up. So this is saying C, the concentration from everything to negative 1, and then subtracting the concentration from 1 to whatever value we want, essentially. And then that is all going to be divided by the volume minus how we want K1 times concentration 1. Now, all right. Lots of chances for syntax errors, so probably not going to get this right exactly the first time. But so now we've done the derivatives for the concentration. Now we need to do the same thing, but for our time. And so for this, dt 0 is going to be equal to, again, our flow rate times our temperature at n minus our temperature at 0. This will be divided by our volume, and then UA, our activation energy, multiplied by our temperature at 0, minus our temperature of cooling. This then will be divided by rho V times C. And then we will be adding our negative heat of reaction. This is because it is exothermic. Times our K value at 0. Times our concentration at 0. Divided by rho C. Whew. All right. Lots of typing there, and we have one more equation to do. And I'm sorry, these actually need to be capitals because when I define them, they're capitals. dt, this is from 1 on, and this is going to be, that is not exactly what we're looking for, so we're just going to type this out. This is going to be T. I'm reading through this to see if we actually can use this or not. We actually can, but it's just not complete. So that is correct, but now like this one, we can use this negative heat reaction, except this is not going to be 0. This is going to be 1 on, obviously. And same here. All right. Now, obviously, all this work is for nothing if we do not return any values. So we're going to return np r underscore our dc and our dt. Run. Wow. Very surprised I did that without typos, but hey, I guess the more you do it, the better you get. All right. So all of this coding that you can see is done without jacks. And now we are going to utilize that jacks as requested in the problem. And honestly, it's just more helpful. So we again have our right-hand side. But now we're going to be integrating this jacks component. And we want t vector. And now we are able to do all of this in jacks. So we want c, we want t. Now, it's suggesting np.split here. This is correct, except that we're using jacks. So now it's jnp dot split. Okay, and now as you can see, it did suggest it correctly, but then it went away. We want that. Please do that again. I guess it doesn't. Oh, here we go. It goes away. Why does it do that? Oh, okay, whatever. We'll type it in. DC is going to be equal to, that's what we want, jnp dot zeros n iterations. So this is the same thing as above, as you can see up here, np dot zeros, but now we're using jacks. So we'll tab. And then we also need to do the same thing for our Arrhenius equation. Again, same thing as above, but now jnp instead of np, which that works perfectly. And then dc, I'm reading this, dc dot at zeros. Gemini is on a roll because that is correct. So essentially, the reason that Gemini knows how to do this is essentially machine learning in a sense. It's reading my code above and saying, okay, this is what he wants to do, and now he's doing the same thing, but with jacks. So this is almost correct. So we will do tab there, but this k is going to be from 1. Excuse me. There we go. And now we need to do the same thing with dt. dc. That is correct up to the activation energy. And now our activation energy is going to be equal to, ooh, wow, man. I think it is continuing. Get out of here. That is correct, actually. But then this needs to be multiplied by k. Sorry, not k, or multiplied by k. C 0. Rho times uppercase C. Able to drag this a little bit. No, does not allow me. Okay, that's fine. So we have our dt equation, and then we want to set dt again, which this is correct again, obviously. But now this time it is going to be 1 the reaction. All right, wow. Gemini just saved us a lot of time. And then the final part, again, you gotta return your values. That's one thing that I struggle with. I often forget it. And then right-hand side, jacks, it's jacks, jets. All right, one more definition. And this final thing, we're going to be using Jacobian as we said before, so we will type that in here, which will be Jacobian. All right, let's run this and make sure it's working. Invalid syntax. Explain error. Let's see what it's saying here. Oh, I see it. I see it. I don't even need you. I'm smarter than you, Gemini. This is my... No. Yeah, okay. It's supposed to be a colon, not a semicolon. Accept and run. I tried to beat... Oh, I think I just accidentally went back. I tried to beat Gemini there. Okay, it's green now. So we typed all of our equations in using JAX and not using JAX, and now we are able to start working on our plots. Actually, before we do this, I wanted to give a little bit of framework. So if you don't understand what these equations are actually doing, we can label them. So this is actually doing our material balance for us as DC, and then this is doing our energy balance. And the same thing down here, this DC will be our material balance. And again, this is not necessary to do, but I think the labeling like this, I mean, it definitely gives you a better comprehension of what is going on. So you know why you're just typing all this random, not random, but all these variables, and sometimes you can get lost in that tunnel vision of variables, like, but sometimes you actually forget, well, what does it actually mean? What am I doing? And that's what these DC and DT variables are in charge of. So now we are starting to get to the point where we actually get to see all of this, and we now need to identify our n times variable, just like we did previously. You can kind of notice we're working through the same framework. Like we have our we essentially just completed this portion in the last video. So now what we're going to do is, have this T plot, this res, C profiles, n times. We're going to complete this. We're going to complete this. And then it's going to allow us to make that plot. Just so you guys understand where we're at. So this is going to be 100. And then our dt is going to be equal to our tendencies divided by our n underscore times T plot, per usual, is going to be equal n dot lin space 0 tend n underscore times. And then we also need to still use our integrate, which is sp integrate dot solve underscore IVP. Right hand side underscore JAX 0, not 9. Oof, a couple typos there. Oh my gosh. Okay, sorry, I blanked there. So we have right hand side underscore JAX 0 to 10, and then we also need our np.r underscore c naught and t naught. Again, everything revolves around these concentration and temperature profiles. And then again, as always, method Radu dense underscore output going to be true. All right, and then the final thing we need are our profiles of the concentration. And we need to solve these. t plot. Now, let's make sure this runs. Green check. We are good to continue into the final portion, which will be making all of our dreams and wishes come true. All right, let's get into it. The final portion, which will be plotting. Oh, not generate. We don't want that. Now, we want to plot a C plot and a T plot. And again, the split functions will allow us to do that. Res.sol plot 2. We're setting our axis equal to 0 here. And then we want to separate that from the actual plotting because that's not part of the essential plotting code. Now, back. This is kind of like just going through the motions at this point. Make subplots. I'm like a robot. Rows equal 1, columns equal 2. For t underscore index in range I'm a terrible typer. Absolutely terrible. I don't know why. Like, I type a good amount. I just don't know. There we go. Now, fig dot add underscore scatter. We're actually gonna copy. Now we a range C plot. This isn't exactly right, just from reading this, but we can. No, we're just gonna type out, and we're actually gonna copy this too because we're gonna obviously plot both C and T plots. So in these parentheses, we need x equals np dot a range, not arrange, n. Y is going to be equal to that C plot. Again, so this, we set x equal to the range across the bottom, so that if you imagine it, the y will be doing all of the motion and our x is consistent, so we're actually able to see the motion. Now the C plot is going to be colon, I made that mistake earlier, t index row equal 1, col equal 1. Now we have to actually input this index, which is ft equals dt times t index Now we have to input a legend group. This way we're able to understand what we're reading. Alright, now a lot of this is able to be copy and pasted, so like this XP arrange all the way through here, but we're going to actually change that last number to 2. Again, we need this legend group. Equals false. Sorry. No, legend group equals t. This is so much syntax. I know this is not going to run the first time. All right. So we have successfully created that. Now all we need to do is make the thing. All right. Full transparency. Let's see if it runs. It took a while last time. It took a good 20 seconds to run. Oh. Okay, I'm gonna look through these errors and I will be back. Okay, I adjusted the camera so you could see this a little bit better. I fixed the error, obviously. The error was up here. I had SP instead of NP. Super simple fix. Now, actually, I have an error. I think I have another error. Sorry, dang it. These are supposed to be different plots. Give me 1 second. All right, found the issue. Copy and paste is a dangerous thing, and I don't recommend it. Here, when I copied this line down to here, I accidentally put C-plot and C-plot, so it just plotted the same thing twice. But now we have our C-plot, we have our T-plot. Let's analyze. So we have our 100 iterations. Here's the concentration. Starts at 1, and as the reaction continues, as you go down the tube, that concentration drops, bang, like falls off a cliff. You'd be wondering, well, if you were to possibly overlay these, you'd notice, oh, well, that is when the temperature gets really high. This exothermic reaction, when this temperature spikes up super high, it rapidly drops your concentration. The concentration, as you can see, is pretty flat after that point. And then, some of them start to kind of come back up. But at the beginning, the concentration starts high and immediately drops. And since it's exothermic, the temperature starts low and begins to heat up as you go down that tube. That is the conclusion of part B. I hope you enjoyed, and I hope you also watch parts C and D.